good morning everybody. We started already gas turbine systems. Gas turbine we have discussed and we learned that there are different components in gas turbine. One is your compressor, then compressor will be connected to your turbine, and compressor and turbine in between there will be one combustion chamber or combustor. Okay, so this one we have seen, compressor, turbine, this one combustion chamber or combustor. So this way your gas turbine system will be working. Now we will try to discuss about regenerator. What is regenerator? Regenerator means you are using exhaust heat to improve system performance. So how does it work? Let's say first draw line diagram. Compressor connected to one turbine. So then compressor will have inlet air 1. From inlet air it will go to one heat exchanger, then another, then it will go to turbine, and this is power output W turbine, this is turbine, and from turbine the exhaust gas will come and it will be exchanging heat here, then it will go to here and like this. Okay, so this one I will be making one block, this one another block. So 1 to 2 it will go, 2 to 3 it will go, 3 to 4 it will go, 4 to 5 it will go, 5 to 6 it will go, 6 to 1. Now this one is regenerator. I will explain later. First you draw the figure. Heat rejection is happening Q2 here and heat input is happening here. So this is Q1. Okay. Now you draw this one in TS diagram. TS. So TS diagram it will be looking like this. First you have to draw this pressure line, constant pressure 1 to 2. You can see there your compressor is working at 1 to 2 in between, then it will be going to 0.3, then 4. You can see 4 is before turbine. So 4 to 5 your expansion is happening. We are assuming isentropic expansion. Okay. Now 5 to 6 what is happening? 5 to 6 heat exchange is happening. So some heat will be lost or it will be given to your compressed air. So you can see this 2 to 3 and 5 to 6 it is having one regenerator. What is happening? The exhaust gas from turbine, whatever gas coming after turbine, so the gas will be used to heat your inlet air. Inlet air means after compression the air is going to combustion chamber, so that air will be heated up. So waste heat, the turbine exhaust is having lots of energy, it's very high temperature actually, 400 500 degrees, still temperature will be there. So that temperature or the heat will be used to increase your compressed air temperature. After compression the air is compressed, so that air temperature will be further increased and it will be injected into your combustion chamber. So why this increase? If you increase, actually your combustion chamber will be requiring less amount of heat to give to air. Now, or the mass fuel plus air mixture. Okay, so that's why you are using certain amount of heat from exhaust gas to increase your compressed air temperature. Okay, so now the process is happening. 1 to 2 is your compression, 2 to 3 is your regenerator, or regenerator is giving certain amount of, the exhaust gas is giving certain amount of heat to your compressed gas. So but process is isobaric process. 2 to 4 you can see this is isobaric process. So process is happening 2 to 3, temperature increased, and 3 to 4 what is happening? 3 to 4 actually your heat addition happening. So instead of giving heat 2 to 4 you are giving heat 3 to 4. So actually you save certain amount of heat or energy. Now 4 to 5 your expansion process happening, W turbine, and 2 to 3 actually W compressor, and 5 to 6 you can see 5 to 6 actually the heat given to your compressed air. So, that compressed air means 2 to 3 the process you can see in the figure, 2 to 3 taking heat and 5 to 6 giving heat. Okay. So, 5 to 6 also constant pressure process, 5 to 1 actually, 5 to 1 constant pressure process, and in between 5 to 6 process happening. So, there your heat rejection happening. So, that heat is going to 2 to 3 process. I am drawing one arrow symbol, you can see 5 to 6 the process, that amount of heat is going to 2 to 3. Now, 6 to 1 what is happening? 6 to 1 heat rejection happening. So, normally the air combustion mixture will go to atmosphere. So, for to make this closed cycle, 6 to 1 is drawn as a continuous line. Okay. So, this is called regeneration. So, regeneration, generation. Okay. Now, T5, temperature at 5 must be greater than T2. Okay. So, why T5 must be greater than 2? If T5 is not greater than 2, then heat will not be flowing to your compressed air. From exhaust gas, heat must be flowing to compressed air. So, exhaust gas temperature must be higher than that. Okay. Now, maximum temperature cold air, max temperature of cold air at 2 can be heated in temperature of air at 5, can be heated to air at 5, similar to air, I mean same temperature you can reach actually if it is ideal condition, but practically it is not possible. So, actual case T3 less than T5, actual case. Okay. T3 will be less than T5 because when okay, 5 to 6, 5 temperature higher, 6 temperature lower. Okay, this is, and 2 to 3, 2 temperature lower, 3 temperature higher. Okay. So, 5 means here 6, 2, 3. You can see this counter current heat exchanger actually. We are assuming counter current heat exchanger. Okay, you can see this 6 to 5 to 6 heat, fluid is releasing heat, and 2 to 3 it is accepting heat. Now, regenerator effectiveness, generator effectiveness equals T3 minus T2, T5 minus T2. This formula you should remember. Okay. Now, heat given to the system Q1 equals H4 minus H3 equals Cp T4 minus T3, Q1, Q2 H6 minus H1. You can see this heat rejection, H6 minus H1 equals Cp, again constant pressure process. So, T6 minus T1. Now, turbine work Wt equals H4 minus H5. Okay. So, again Cp T2 minus T1. Okay. So, approximately you can assume constant Cp. Okay. So, for approximation purpose, normally we assume Cp and Cv are constant, and normally the gas gamma value will be 1.4. If no value is given, gamma value of Cp, Cv, so you can assume gamma value 1.1, 1.4. So, W compressor, how much power you are giving to compressor? H2 minus H1, again Cp T2 minus T1. So, now eta equals 1 minus Q2 by Q1 equals 1 minus T6 minus T1, T4 minus T3. So, from there you can calculate your efficiency, your power output, your heat input, your heat rejection. Now, we have seen in area heating, and intercooling happens between two compressors. Okay, let us say compressor 1 and compressor 2, C1, C2. In between there will be intercooling. I'll draw it properly. C1. Okay, so you can see this C1, C2, C1 compressing certain amount of air. Then when it is compressing, because of Charles' law, you can see, you can remember the Charles' law says, like, if you are compressing, temperature will be going up. So after C1, temperature will be going up. So if you reduce temperature, then again volume will be dropping because you reduced heat. Then again you put low volume air into C, then C will be compressing further. Okay, so that C compressed air, C2 compressed air, that will be going to your combustion chamber. Okay, then you will have one turbine or many turbines. Okay, and those turbines will be connected or to the compressors. Okay, now what happen? The intercooler, in between these two compressors, the cooling is happening. This is called intercooler. Okay, during our pumps and compressor section also we have discussed the intercooler. Intercooler means you are reducing temperature so that your compressor performance increases or efficiency of performance increases. So input work will be lower if you are using intercooler. Okay, so here in axial system, in gas turbine system, normally we use axial compressor, maybe axial, and sometimes centrifugal compressor also may be there, but no, normally first stage will be axial compressor definitely. Then you reduce volume, then you can use centrifugal compressor. Turbine, normally it will be axial turbine. Okay, now how this whole system will be working? So we can assume there is your condenser here. Okay, now I want to draw this one on TS diagram. TS diagram, again, when you are drawing TS diagram, you have to draw pressure line first, then you have to put number 1, and then after compressor 1 you are giving 2, after intercooler you are giving 3, then after compressor 2 you are giving 4, then combustion chamber after 5, after turbine you are giving 6, then your heat rejection. Okay, so Q2 here, Q1 here, and turbine work WT minus WC equals W net. Net work output you are getting W turbine minus W compressor. Okay, now in TS diagram 3 to 4, you can see 3 to 4. First 1 to 2 compression will be happening. Okay, 1 to 2 compression happened. Then after 2 intercooling happening. Intercooling happening means pressure you are not changing, rather you are changing temperature. So what will happen? Your process will be downwards towards T. Then 3 to 4 again compression happening. So temperature going up. Okay. So 2 to 3, 3 to 4 happened. Now 4 to 5. 4 to 5 means you are adding heat. So 4 to 5 means the whole process is like this, then 5 you reached. 5 to 6 your isentropic turbine expansion. So 6 to 1 again your heat rejection process or constant pressure process. Okay, so this line P equals constant, this is also P equals constant. Okay, now if I draw this one a PV diagram, so it will be like this. 6 to 1 is a constant pressure process, but it is near to atmospheric pressure, right? So 6 to 1, so 1 to 2 what is happening? Compression happening. So 1 to 2 compression happening. Then 2 to 3 actually your pressure not changing, rather heat rejection happening. So volume will be reduced. So volume reduced. Then 3 to 4 again your compression happening. So compression, adiabatic compression. So it will be like curved. So 1, 2, 3 to 4. 4 to 5, what is happening? You see 4 to 5 actually constant pressure process, because inside combustion happening, but pressure 4 to 5 will be same. So, 4 to 5 year compression process. Okay. Now 5 to 6 turbine expansion. So, it will be adiabatic process. So, it will be curved line actually. Okay. So, turbine expansion process, W turbine, and compression happening here, one time your compression happening, another one time compression, like C1, C2 you can say. Okay. And 4 to 5 your heat addition process. So, here I can write Q1, and 6 to 1 heat rejection process. So, I can write Q2. Okay. So, because of intercooling, you can see certain amount of energy is saved actually. This dotted line I am making, this lots of dot I am putting there, this part actually energy is saved because you reduce temperature. Okay. So, 1, 2 dash, I can put here 1, 2 dash. In TS diagram I put 1, 2 dash. Okay. 1, 2 dash, 5, 6 ideal cycle without intercooling. Without intercooling, but 1, 2, 3, 4, 6, 1, 2, 3, 4, 5, 6, 4, 5, 6. So, that will be with intercooling. Okay. So, when we are going to without intercooling, we are having more, we are using more energy to get certain amount of work. Okay. Now, what is the purpose of intercooling? If I draw, if I have, let's say, multiple stages of compressor, compressor 1, compressor 2, compressor 3, compressor 4, many compressors are there. So, if we have many compressors, actually we will be trying to achieve our isothermal condition. If we have isothermal system, that will be having the best efficiency. Okay, the whole system. So, P, V, and let's say this one my system. Okay, actually this is isothermal dotted line. This is adiabatic. Okay, so if certain process is adiabatic in our system, so that system will be taking more energy, so performance will be lower. But if I can achieve isothermal system, then my system will performance will be better. So actually intercooling will try to match towards isothermal condition. Okay, so but in practical situation we cannot make many compressor one C1, C2, C3, C4 like this. So maybe 2-3 stages we can limit, and we can get some optimal performance. But if we can make, let's say, 100 to 100 stages like C1, C2, C3, C100, then actually we will be achieving almost isothermal condition. So, reheat with intercooling, how it will look like? I have one compressor, I have another compressor, connected, turbine. Now, compressor 1 is having input here 1, 2, 2 to 3 you have intercooler. Okay. Then 3 to 4 you have combustion chamber, Q1 coming, 3 to 4, 4 to 5 is your heat addition process, 5 to 6 again reheating process happening. Okay, it will take heat, again it will go to turbine 2, C1, C2, T2, then going like this, then going, coming here, then coming out, 5 to 6, six to 7, 7 to heat rejection, it is going to again 1, 7 to 1. Now if I draw this one in TS diagram, first I have to draw the pressure lines. So 1 is here, 1 to 2 compression happened, so vertical line, because we are assuming ideal cycle, isentropic cycle. Then 2 to 3, 2 to 3, what is happening? Heat rejection happening, so that's why temperature going down. 3 to 4 compression happening, 4 to 5 heat addition happening, 4 to 5 heat addition happened, 5 to 6 turbine took certain amount of power, 5 to 6 will be here, not here, 6, 7, it will be 8. Okay, 5 to 6 will be turbine will be giving some power. Then 6 to 7 actually again temperature increasing but constant pressure. Then again your expansion happening, 7, 8. Okay, not this one, this will be opposite way, this one, this one, this one. Okay, now you can see 1 to 2 compression happening, so this is C1 process, 3 to 4 C2 process, 4 to 5 heat addition process, 8 to 1 your heat rejection process, 6 to 7 reheat cycle, reheat. Okay, and 2 to 3 your intercooler. Okay, so intercooler and reheat cycle in one figure in TS diagram you can see there. Okay, now if we consider one regenerative cycle with reheat and intercooler, how it will look like? Again you draw compressor 1, compressor 2, it will be connected to turbine, expansion. Okay, now C1, C2, T1, T2, W net equals W turbine minus W compressor. Now C1 getting air 1, C2, C1 to C2 there will be intercooler. Okay, so I'll be drawing one box here, one coming like this, going like this. So this is intercooler. Okay, now C2 to T1 there will be one heat addition process. Okay, the combustion chamber or combustor. So combustor to turbine 1 to turbine 2 there will be reheat process. Okay, so I can make another reheat process. Okay, reheat. Okay, so reheat maybe Q1 dash. Now Q1 dash to T2 it is going. So T2 I'll change something here. This line I'll draw opposite way, it will be more clear then. Okay, so T2 to coming here, from here to 1. Okay, now it will be more clear. 1 to 2 it is going compressing, 2 to 3 one intercooling happening, 3 to 4 your compression again happening, 4 to 5 what is happening here, regenerator. Okay, so regenerator is giving heat to your compressed air. Okay, so after compression your heat addition will be happening. So Q1 you are giving heat here. So then 4 to 5, 5 to 6, 5 to 6 actually your combustor. 6 to 7 your turbine 1 expansion process, 7 to 8 your reheat process, 8 to 9 your again expansion process, 9 to 1 regenerator is happening. Now whole thing I want to put in TS diagram. How it look like? First you draw main pressure line. Okay. So 1 to 2 compression happening, 1 to 2, 2 to 3 some heat rejection happen, 3 to 4 again compression happen, 4 to 5 what is happening? 4 to 5 some heat addition happened. Okay, so 4 to 5 heat addition happened. Then 5 to 6 your combustion chamber worked. Then 6 to 7 expansion worked. Okay, 7 to 8 again reheating happening. Okay, 7 to 8 reheating happening. Then 8 to 9 again expansion happening. Okay, now you see the process. So 1 to 2 compression happened, 2 to 3 intercooling or heat rejection happened, heat rejection happened, 3 to 4 again compression happened, 4 to 5 your compressed air got certain amount of heat from your exhaust gas, 5 to 6 your turbine combustion chamber is working, 6 to 7 turbine worked, 7 to 8 your reheat worked. So this is Q1 dash some heat you have given, 8 to 9 your turbine 2 work. So this is T1, this is T2, this is C2, this is C1. Okay, this way you can draw your TS diagram. So the regenerator effectiveness, because actual temperature rise divided by maximum possible rise. T5 minus T4 divided by T9 minus T4. Okay,